this is Bronwyn.
And Aaron.
And we're here to talk to you today about Week 3's prac for LQB 481. So today we're looking at accuracy and precision in biochemical assays. This is really different today, isn't it?
It is. So, what are we doing exactly?
We are going to use a Bio-Ret assay, and that assay will allow us to measure the protein in the sample. And we're going to look at BSA sample, which is just protein.
So, we're going to be doing this in tenfold replicate,
Yep.
I do believe.
Yep.
But before we get into the nitty-gritty of the experiment itself, I'd like to discuss hypotheses.
Of course you would. We all love our hypotheses.
We
don't
do.
we?
So, in science, there are good and probably not so good hypotheses. What would you say, in regards to a hypothesis, would be a good hypothesis?
Okay. So if we were looking at milk samples and we were measuring the lipids in a reduced fat sample and in a full cream milk sample, a good hypothesis there would be simply to say that I think that there's going to be a higher lipid concentration in one or the other. So of course we all know that there should be a higher lipid concentration in the full cream milk. So my hypothesis there might be that there is going to be a higher lipid concentration in the full cream milk.
That sounds good. Whereas if I hypothesized, and this is going to be a bad hypothesis, that if I do correct pipetting, I'm going to work out how much lipid is within my sample, that's not so great. It doesn't add any merit to the actual science of the experiment. Remember, a hypothesis needs to be a testable statement about the experiment itself, not about you as a scientist.
But in this case, don't forget that the main aim is actually the accuracy and precision. So you may want to think about that in terms of your hypothesis and not so much about the BSA sample.
So, the main reason that we're doing our replicates for today in checking for the accuracy and precision in regards to a standard is to show that how possibly error is introduced. What is one form of error which could possibly be happening with this particular assay?
Pipetting.
Definitely. I know that after many, many hours, my pipetting skill is amazing. You'll get there one day. What about you, Bronwyn?
Oh yeah, mine's amazing too.
So, in the experiment, we're going to be required to make up a blank, make up a standard, and then our 10 replicate samples. We will then be using a spectrophotometer to take readings at a particular wavelength, and this data will then be compared to the standard to determine how accurate your pipetting is and the precision.
Our lab technicians were really kind and they let us film them while they were setting up for the prac. And you can see here they've got all of their bottles out, they've got their tubes, they're all labelled, and so everything is ready to go. They've got their pipettes already prepared, they've got their tips sitting out. So now we'll watch them set up a test sample. So here we have the
P1000, and they're taking 200 microliters of water into their Eppendorf tube. To this water, they're going to add 50 microliters of test sample using a P200.
Watch their pipetting technique while they do these things. It's always good to watch other people's techniques to see if you can improve.
Definitely. And finally, 1 milliliter or 1,000 microliters of the Bio-Ret reagent. Now, make sure you seal the tube and give it a good mix.
And there you have it, your sample's made.
Alternatively, you can also use the benchtop vortex.
What happens when we use the vortex? And you have to make sure that it spins completely up the sides. If it just bounces around, it's not going to mix properly. So if you're using it and you're not sure about your technique, make sure to ask your demonstrators, because they all know how to use them and they'll be able to tell you if you're doing it properly. So if we have a well mixed sample, what are our set of results going to look like?
Here is a comparison of our blank, standard and test samples which have been prepared. As you can note, there is a colour difference, and this difference is what is being measured by the spectrophotometer.
So these tubes are lying on their side, so that's why their volumes don't look the same. But you can make sure that your tubes are all the same by holding them up next to each other, and the volumes should be identical. And you can do that all the time when you're doing assays. It's a good way to check to make sure that you haven't done anything wrong and that you or your partner didn't use the wrong pipettes when you were preparing the solutions.
It's very important to note that. When using the spectrophotometer, you might encounter some results which look like this, where it basically looks like you've only got noise. This is primarily due to the machine's detector not being set correctly, as can be noted by it being set to microvolume rather than accurately being set to cuvette and millimetre. And we have a spectrum which actually shows some results.
So if you're getting really low results, that's one of the first things you should check. Of course, if you still can't figure out what went wrong, make sure you speak to your demonstrator. There's nothing worse than having a student at the end of the day say, "We didn't get any results, we've measured all 10 samples and we got nothing." And by then it's too late for them to get a beautiful set of results. So if something's going wrong, make sure you speak to your demonstrator, because they'll be able to sort them out before you get to the end of the day. Here are some results for the practical. These were done by a laboratory technician, and you can see that we have a 0 for a blank, which is exactly what you want. Then we have the standard solution. The absorbance was over 0.5. And then we have our 10 samples. And if you have a look at the samples, you can see that they range from about 0.45 up to a bit over 0.46. So these results are quite close. And we have also shown them to you in a graphical format so that you can get a better idea of just how close they are. Now, we know that our picture is hiding some of the results from you, but they are all around the same number. If you wanted to go back and look at the Excel spreadsheet, you can see that they're all around the same number.
Whilst you don't have to prepare a graph like these, it is recommended that you do the statistical analysis to determine the standard deviation, the mean, the confidence interval that your data falls within.
And so all of those will help you determine whether your results have been precise
and accurate.
Don't forget that you should be doing everything that's listed in your prac book for the experiment. Here we have the statistical equations that you'll need to do. These are in your prac book, and so make sure that you go through them all and do every single one that you're expected to. So if we scroll further through the prac book, you can see that there's a lab book completion checklist, and this is just a little list of the things that you should be doing to make sure that you maximise the marks you get for your prac write-up.
Ensure that your graphs and tables are numbered and titled accurately.
So that means if you have a graph, you don't call it graph 1, call it figure 1.
Effectively in science, either things are a table and everything else is a figure. These include flowcharts, graphs, calibration curves, and even images that you may have sourced from elsewhere. Finally, we'd like to remind you that your conclusions and discussion should be more than one sentence. You must give a thorough analysis of your data and sum up your conclusions. Anyway, we'll see you in the lab. Bye.